Hello, everyone, and welcome to Innovation Coffee, brought to you by ARM. My name is Robert Wolf, and I am your host for today and every Thursday. In fact, today we're actually going to be, it's not Innovation Coffee for me, it's Innovation Energy Drink, because I just kind of felt like something a little more refreshing. Anyways, today, cheers. Hello, Potting. Hello, Carlo. We have a great episode planned for you. I want to, of course, apologize for last week. We had to cancel last week's episode. We don't do this that often, but every now and then it does happen. But today we have a great episode planned for you. In fact, we're bringing in Richard Elberger, who's the IoT principal technologist at AWS, otherwise known as Amazon Web Services. So he's going to talk to us about all the cool things that he's been working on, as well as most of today's session is actually going to be a teaser for the ARM Dev Summit session that he's going to be presenting. So lots of cool stuff that will be kind of teased. There's going to be hopefully a demo teaser as well. Yeah, so we'll get to know our guest in just a moment. But as we usually do, we do a recap. I don't know why I said that, because we canceled last week's episode. So we're just going to dive into the news. How about that? If you can't tell, I'm super excited to be back in action, right? Like after the cancellation. But so news today, same as the last few weeks. In fact, Dev Summit, ARM Dev Summit is right around the corner, starting in October. I believe it's October 19th, 20th, and 21st. So mark your calendars. If you haven't already registered, we're going to put the link right down here, devsummit.arm.com. It's coming. It's a banner. We can click it. Boom, there we go. Oh, she got it. Okay, devsummit.arm.com. Head on over there, register. There are so many cool sessions. There's like hundreds of things to do all day. You can get tech sessions, keynotes, panels, workshops. And this year, the workshops are actually free. So you can just pop in, start building cool stuff. Of course, there's all sorts of community engagement opportunities. We're going to have a spatial chat where you get an avatar. You can go around all these different cool little stages and talk with your fellow attendees. We have a new Discord server that we launched, of course, so that when you're around the event, you want to go hang out with some people, you can go to the Discord server, and there it is scrolling across right here. Lots of cool things that you can do. Make sure you check that out, devsummit.arm.com if you aren't already registered. Another thing to kind of update you all on is we have the Dev Summit, ARM Dev Summit competition. So the ARM Dev Summit competition kicked off, I think, like a month and a half ago now. So here it is. Sustainability is our goal. So you can go check that out. I believe if you are a handy developer, you can probably still get in there and kickstart your project and get that going. Maybe submit it in time. So definitely go check that out. That's developer.arm.com/Dev Summit-competition. Lots of prizes to give out. Lots of cool stuff going on there. Now, before we go into introducing our guests, I want to remind everyone that if you enjoy this stream, don't forget to hit that like button down there on YouTube. It helps us out a lot. Subscribe to the ARM Software Developer YouTube channel, because you can get updates and notifications when we do these types of live streams, every single week. And, if you're watching this and you have any questions for our guest, you can just post that in the YouTube chat, right? Like we're reading that chat. We'll bring those questions on so that you can ask our guest, and we'll get those to him as soon as possible. Now, I think without further ado, it's time to go in. And I'm getting actually some notice here that maybe my mic is a little choppy. I'm wondering maybe if it's clipping because I have this set up too high. We're gonna try this. We're gonna sit down a little lower. Okay, so let's welcome in our guest. Richard Elberger, welcome to the show, and hello, Richard. Innovation,
hey there.
Energy drink, innovation coffee. Cheers here. Cheers, my friend. Here you go. So this is your first time on Innovation Coffee. Hopefully you see this is a nice little casual hangout among friends, among fellow developers. We want to get to know you, of course. So before we dive into the topic at hand, maybe you could tell us a little bit about yourself. Give us like your origin story.
Yeah, sure. So look, it really started a long time ago when my dad got a computer in 1978. I was 7 years old and first connected to the internet there in 1981. Well, it was just like such early days, right? So it's called something else back then, but that's close enough. And then I've been using Linux now for over 25 years. Back then, you could even think, well, that's kind of like embedded Linux. Back then, anyone remember installing Linux at that time? You're like installing files from floppies and stuff like that. But then we got lucky. Things got luxurious with distributions like Debian. So we were able to lay back and just install stuff, install your distribution and have fun. But now for like, I don't know, like the last 10 years since Yocto project came around, customers have been formalizing the way that they work with embedded Linux. And that's really what I've been working on for the last 5 years here at AWS, working with customers and partners, and now in a more formalized way with some additional delivery vehicles we'll talk about later for embedded Linux. And it's just super exciting.
Excellent story. I love it when people date themselves, like, because I feel old among a lot of, like, my colleagues and stuff. I wasn't even thought of when you were getting your first computer and tapping into the internet, right? My parents didn't even know I was on the way. And I'm 36, right? So that's really cool. It's always nice to kind of get these experiences from people who have been around longer than us. So thank you so much for sharing that. Very nice. Now, we got to go into you, and now we get to hopefully go through a segment that we call Innovation Coffee Cribs. I'm going to ask our producer behind the scenes to cue up that video because we want to see what your crib looks like. Oh, we're on point with these segment videos clips. Hopefully my mic sounds a lot better now, by the way. Thank you for pointing that out, Potting. It was actually set to my Logitech camera here and not my microphone. So Richard, this segment, what we do is we do the Innovation Coffee Cribs. It's like play on the MTV Cribs. But we look at like what developers have on their desks. And I'm hoping you have some cool tech on your desk that you can show and share with us.
Yeah, I have a few things here. I mean, when I'm working on projects to help build stuff for our customers on embedded Linux, there's a few boards I've been really using lately that are really exciting now. But at first, I want to show you one that I consistently use that I started using a few years ago, which is the Renesas R-Car. This is the one that I first started learning about the technology we're going to talk about today, which is the asymmetric processing. When I looked at the block diagram of this one, it was 4 Cortex-A's, and I was like, wait a second, what's that Cortex-R doing there? I just didn't understand at that time. And this is really what started the journey, was this one. But I still use it a lot for automotive grade Linux. Now, this one I've been using for maybe the last 5 months since it was released, which is the new Xilinx board, which is the KV260, right? So this also has a Cortex-R on it, by the way. But of course, it also has the Cortex-A's for the application processor cores, and also the famous Xilinx FPGA fabric, right? Now, when I'm working with the automotive stuff, what's also on my desk consistently is this Jacinto J7 board. So I'm using that on a weekly basis to run some projects. I have the camera angle weird, but all these different things are so you can configure peripherals that run within the vehicle. So when you're thinking about CAN bus or video or audio or any of those things that you normally see in a video, you can prototype with this board. Now, for most of the asymmetric processing prototyping I've been doing for the last 4 to 6 months, I've been using this board right here, which is the Texas Instruments AM64XX EVB. Now, this one is really impressive when you're talking about asymmetric processing. This has a couple of Cortex-A cores, 4 Cortex-R cores, a Cortex-M4F, and a Cortex-M3. Plus, it has some specialized cores on there for the industrial protocol parsing. So you have the PRU ICSS cores on there as well. So those are the ones that I really have on my desk for everyday use.
Those are some big boards. I mean, I feel like that would take up 3/4 of my desk if I had those on there.
That's what when we're doing prototyping, when we're thinking about using a processor, we're using like the tinier form factor boards, like just to get the processor running and see if it's the right fit for me or fit for you. And when you're taking your prototyping to the next level, you need access to a lot more peripherals, right, for building your solution. So in order to do that, you need bigger boards.
Absolutely. Yeah. And I was looking at those boards that you were pulling up. I was trying to kind of like pin down if there were any standard footprints that I noticed. I didn't really notice any standardized footprints there. So they kind of looked like more one-offs or custom boards that I haven't seen those before, but very cool. And thank you for sharing those with us. Nice.
Yep.
So that concludes our innovation coffee cribs, but I do want to ask one other thing here. So of that hardware, will we experience any of that hardware during your Dev Summit presentation?
So yeah, so this is, like I mentioned, this TI board here, which is the AM64XX EVB. This is the one that's going to be running the demo. Right?
Nice. Okay.
So it's just because you have so many cores to play with, you have so much to demonstrate. So this is exactly what you're going to see in action during that demo.
Very nice. Very nice. Thank you. Thank you for sharing that. Again,
Yeah, sure.
This is an episode of teasers here, so you're just going to be teased. All right. So let's dive into the main segment now. You know, we're about 15 minutes into the show. Tell us a little bit about your work at AWS, because I think this is going to kind of lead us into, you know, more talk about this session that you're going to be showcasing. So what do you do at AWS? You know, what kind of fun development are you working on over there?
Yeah, sure. So, you know, the title technologist can seem a little bit fluffy sometimes. And I'm actually situated within the devices team within AWS IoT. So when you think of software solutions that AWS provides to customers, such as FreeRTOS, the embedded SDK, device SDK for embedded C, AWS IoT Greengrass, they all come out of that team. And it's really my responsibility to ensure that I'm not only socializing these solutions on various partner hardware solutions, but I'm also receiving back feedback from developers. It's really about developer experience, getting back the developer experience, cultivating that, and then putting it in a way that our own developers can consume that and make the solutions better for our customers. So that's my day-to-day. When you see me out giving talks or writing blogs, it's really to get the message out there and solicit feedback actively.
That's huge, I have to say, and you know, kudos to you and AWS for actively seeking out feedback and working with developers. I think that's a huge thing to do, right? And of course, you know, when you look at some other aspects, and we'll talk about this of your session, FreeRTOS, right? Like from Amazon, open source. Also something I can imagine that solicits a lot of help and feedback from developers. So I think it's right up your alley. This is a really cool, I'm looking forward to talking about all these other aspects here. So you talked to us about your role there at AWS. Now let's dive into kind of the meat here, your session at ARM Dev Summit. So can you give us kind of like an overview without spoiling too much? What is this session about?
Well, look, this is really, when I'm presenting it from a technologist, like what my role is, I'm speaking with people about technology, how to run AWS device software, but I'm also talking about the art of the possible, right? So look, let's just make it simple. Asymmetric processing has been around for a while. It's not something that came out last year. I think it's like going on a decade or more, right? Coming from ARM, these types of techniques, I think even longer. But I'll be straight with you. I mean, it's still like not easy for someone to go in and start thinking about how to implement a solution with these processors, right? We have concepts from a technology perspective. Other folks have ideas of maybe what they could do with the technology. From a solution perspective, bringing it together and then having a programming model or set of techniques or set of patterns to understand how they can go in and implement solutions faster, safer, and integrating with the cloud even better. This is really the message that I'm putting out there. And look, it's first you have to explain, well, look, we have all these cores in here. Why are we doing that? Why do we have, you know, Cortex-M smashed up with Cortex-Rs and Cortex-As all together on the same die? Why is that important? And I get into that in the talk. And really what as it progresses, it's like, okay, now we have this, we understand why it's there. How do we capitalize on that, right? So
So I want to, a quick question here, right? Like if you go look at the abstract that you talk about from design, and then there's this transition for implementation. So can you kind of like give us a little bit of a, like, what do you mean by that? Where does the design start and end? Where does the implementation start and end?
yeah, so I have some cheat sheets here. So let me bring up this guy here. Let's try getting the camera, but you have like this processor topology, and this is when you're picking a processor that is a heterogeneous processor topology like this. You're not just going to go and pick one and say, okay, I'm going to use that. The whole purpose for these guys is to ensure that you're picking a core mix that meets your use case, right? So if you have a use case and you don't need something that requires hard real time, then you're probably not going to pick a core that has a lot of Cortex-Rs in it, right? So the first thing is what do you want to achieve in your use case? You have to understand your use case very deeply, and then you can go and narrow the processor dies that you need to achieve that. Now, once you do that, then you can start thinking about design patterns, and especially when you're integrating with the cloud. And there's a few design patterns when you transition from the hardware, the systems solution, and then into the actual application design. Then you need to start thinking about application patterns. And this is, again, what I kind of talked about at the beginning, which is, well, it's been around for a while, but it's still rough days about applying these larger concept patterns that it's simpler. I'm not going to call it easy because that's kind of like debasing it, but but at least make it simpler to think about in terms of larger building blocks and applying these patterns to solutions that I keep on hearing about from customers that they're doing, and trying to make it easier to approach and then integrate that into solutions that need to work with the cloud. So
Yeah. Yeah. Cool. Well, I think you summarized it there. It definitely made sense for me. I hope for the viewers. If not, catch it on demand, rewind, and re-listen to what he did and showed that little diagram there. So let's go into some of these terms, right? Because we are throwing around quite a bit of jargon, and we don't know if there are any beginners on the call. So let's make sure we kind of cover all the bases here. You've thrown around terms like heterogeneous multi-core. In the description of your session, you mentioned heterogeneous multi-core patterns. We've talked about kind of embedded Linux, FreeRTOS. This is also mentioned in your session abstract. So can you kind of maybe give us like a little summary, bird's eye view? What are these terms meaning, and how are you kind of utilizing these terms in your session? How will you be kind of talking about them?
yeah, it's really challenging because even looking at academia for the last decade, there's a huge mixture of the way that these terms are utilized, like heterogeneous multi-core, heterogeneous many-core, all these sorts of things. So it's really challenging, but I can actually make it really simple. If you look at something like, I'm trying to dig out my Raspberry Pi because it's really rare that I use this thing, because I have all this other stuff to use. But when you look at a Raspberry Pi, this has, I believe, well, this is a 4, so it's either has, I'm pretty sure it has 4 cores, right? So 4 Cortex-As. Now, if it's a die that has only 4 Cortex-As in it, I'm kind of cheating a little bit because I think that there's also something else in there. But that is what you call a homogeneous core set, right? They're all the same type if they're like 4 Cortex-A72s or 4 Cortex-A53s. Now, it gets a little bit challenging when you have, like, for example, 2 Cortex-A53s and 2 Cortex-A57s, and then you start having like a big little type of architecture. When you need to amp up the power, it flips up to the A57s. But I can still pretty much say that that is really a homogeneous architecture, right? Because you're just doing symmetric processing among those cores. Now, when I talk about heterogeneous multi-core, what I mean is that you have the Cortex-As, which are running with a symmetric behavior, and they have cache coherency and all this other kind of stuff that you need to run an operating system like Linux. But then you have other cores on the die that somehow this operating system called Linux needs to communicate with these things to make the system effective, right? So you'll have like Cortex-Rs, which are the hard real-time processors. You'll have Cortex-Ms, which are still pretty darn good, but they're not, they don't have those hard real-time constraints. So when you're running a die that has those heterogeneous set of cores, you have Cortex-As, Cortex-Ms, Cortex-Rs, right? All these different, when you hear these different families, you should think automatically heterogeneous, right? And then they somehow need to communicate with one another. So that's a heterogeneous topology.
So yes. Okay, great. This
Does
makes
that
sense.
distill it, or did I make it worse?
No, I think it totally makes sense. Let me see if I can bring it down even a little simpler here,
Okay,
right?
cool.
Yeah, so you have all these different types of cores. Some cores are intended for, let's say, real-time processing, like the Cortex-M, the Cortex-R, and some cores are intended for more compute-intensive processing, like the Cortex-A, right?
Yep.
And so like a Cortex-A based system, like a Raspberry Pi, can run a full-blown operating system. A Cortex-M based system might be better as like a microcontroller, something like an Arduino. And so you have these Cortex-Ms that can, do all sorts of cool stuff. You have the Cortex-As that can do all sorts of cool stuff. What happens when these two types of cores end up in the same place? And you want to make sure that this single system that can perform best, they each do things the best in different, they each do different things best. How can you make sure that these cores that are in the same system work efficiently together?
Yeah. Especially in safety situations, right? This is what you're calling, many people actually call this even a mixed criticality type of system, right? Where Cortex-A will be running workloads such as Linux and actually running user's the wrong word, but running applications, right? They could be system applications or whatever. The Cortex-Ms or Cortex-Rs are doing something much more specific, like sensing in real time. It's real-time work, right? So sensing in real time, motor control, all these other kinds of things that require very precise timing. And so they're working together across shared memory at that point. And that's how they speak to one another.
I worked with a professor, like, quick tangent off here. I worked with a professor at my university, my alma mater, UCSD. And he might still be developing this, but it was like hearing aids, right? And hearing aids actually are required to be super, super quick. So, sending in analog audio right through the DSP, you need, I think, like a 30 millisecond or 20 millisecond, like that's like the max. If it's more than 20 millisecond processing, then you're going to get an echo. It's not going to be good. So, using the DSP, you basically take this audio, funnel it through the DSP, get the quickest possible turnaround. But he also wanted to make sure, so he was using one of the Snapdragon devices. So there was also some Cortex-A there. So there was a DSP and Cortex-A. And so like he would take the audio, throw it through the DSP, and then get you what you needed to hear. But he also wanted to take your location information, other various bits of data. He wanted to process this so that your hearing aid would communicate with your cell phone and then allow you to set filters for various, things in your environment. And these are types of things that require a little bit more compute intensive processes, right? And so he would use the Cortex-A for certain things, then he would use the DSP for certain things. And these were two separate systems that he had to utilize and have communicate with each other appropriately, right, to maximize that efficiency. I don't know if that's that's not probably a use case that you're looking at, but
it is. But yeah, from a high level, I think what's important is what you just brought up was one of the patterns that you see, which is you see the same thing in machine learning with video pipelines, right? So you need to do some processing really quick on a GPU or an FPGA, and really they're the best suited to do that kind of processing. And it also alleviates processing overhead from the application core, so it can do other things. So,
Excellent. Yeah. So I think this brings us into a perfect segue here. And we talked about this in the green room. Please forgive me if I phrase it wrong, but I'm hoping you can provide us with a bit of an industry background on this transition from simple discrete systems to what we're talking about now, these heterogeneous compute technologies. What can you tell us about this? Why are heterogeneous multi-core platforms so important today versus before?
Yeah, so there's really two reasons for this. One is footprint on the die. You kind of alluded to that during earlier on, right? The different footprints and all that kind of stuff. But really, just think if you had all these cores on different chips on your PCB, your solution size, your design is like much larger, right? And the other piece, key thing for that is actually just simplicity in design overall. I mean, before you would have to, if you're designing this yourself, you would have to piece all that together. Plus, it would take extra energy to run, harder to communicate because you would have to communicate over serial or some over other protocol. Now it's way simplified. When you put it all on all the same die, you can connect all those through main memory, and then you can just communicate over that and save a lot of energy and heartache. So that's why we're progressing towards that. But what I also want to make sure that folks understand is that just because you go out and you find a processor that has all these different cores on it doesn't mean that it's right for you. So I kind of inferred that these are use case, they're targeted towards use cases, right? Like, so the AM64XX EVB that I'm working with that has all those hard real-time cores, that's for industrial, okay? When you're looking at the KV260, they're really talking about that from a machine learning perspective, like things like object classification, like security cameras and stuff like that, right? When you're looking at automotive, that's even different. It's really a lot of messaging, real-time processing across the CAN bus. So these different types of heterogeneous cores are fit for purpose for certain use cases. Otherwise, you could end up getting a core or a processor and only using half of it, right?
Yeah. Yeah. Absolutely. Yeah. And I mean, you did mention kind of like the footprints, right? And, I can only imagine if you're trying to get these different chipsets on the same board, you're talking about power management and all the different other things that are required, right? To get a chip on there. So yeah, the footprint can grow substantially just by doing that.
Even interference, right? So you can
Oh
get
yeah.
interference across the PCB and then all sorts of weird stuff can happen. This really removes a lot of that uncertainty. So
Yeah. Awesome. Awesome. I'm getting excited for this talk, and I don't even really do these types of things, but I'm getting excited for this session you're going to have. All right. So you kind of already kind of gave another segue here. It's kind of perfect. But we want to talk about use cases now, right? And I kind of gave like a very vague use case about a hearing aid, but maybe you could share, what are these heterogeneous multi-core platforms kind of generally used for? What might the average person see around them? Like, they're just like, oh, I had no idea that was a type of system we're talking about today in my living room. What are these types of systems, and what are some use cases that you might share with us?
yeah, so like a lot of the real popular ones today, for example, the Nvidia stuff. Unfortunately, I don't have the opportunity to use the Nvidia stuff often, but I know about their ports. I mean, they have GPU paired with the Cortex-A's for the application processing, right? And that's really a lot of that is used for machine learning type applications, things that require a lot of math to be processed very quickly in order to do object classification, for example, or other types of inferences that need to be done, especially pipelining all the video. So that is really, when you think of the type of core that you work with on that, and that's really here on this topology, you see the, my fingers are messed up. The accelerator here, it's accelerating for machine learning, right? That's what, and then the Cortex-A works with the accelerator over shared memory in an asymmetric way. And so that is, the technology is machine learning, but the application can be autonomous driving, right? For example, so you can put one of the NVIDIA processors in an autonomous driving vehicle, and it can do object classification and that's basically detecting objects on the side of the road or an individual walking across the street, maybe even a dog coming across the path, right? And it's not just about knowing what the object is, but being able to transfer the result quickly so the vehicle can do something about that. That's one case, right? Another case, a good case for the 64XX CVB that I keep on talking about is motor control. And this can be used in a safety critical situation. So when you think of an industrial setting where you're maybe fixing or cutting a lot of different parts, and there are humans around, it could detect that there's a problem or that the motor is overheating or there's a lot of jitter, something like that, and do a safety stop really, really quickly. And that's why those Cortex-Rs are there, so they can behave in a fashion that you require. That's the key case. So for industrial. And then,
Yeah.
of course, if I could come up, how about I leave it at that and see if you have any questions on these?
Well,
cases.
I actually wanted to talk about robotics, right? I mean, we kind of
Okay.
hinted at this like industrial, but you know,
Sure.
one of our guests here, Hybotics, is bringing up robotics. And you know, in school, I remember taking a robotics class, in fact, and one of the big things was, you know, robots. What do? They sense, process, react. Sense, process, react, and there's this cycle, right? And you know, thinking like, we need to really draw the difference, right? Because you can make a robot that senses, processes, and reacts with two separate devices. You can have the Arduino doing all the sensing, and then you can have it send that information to a separate board that does the processing and then send it back to react, right?
Yes.
But again, we're talking about all of this stuff on the same die. So it is quite different. And yeah, defining that is a little different.
You wouldn't think that, oh, I'm just transmitting electricity over wire. It's not going to be that slow, right? But it can be latent and error prone, right? A lot of things can happen. Even the wire could break, and then you're out of business. So the cool thing about what you just said is, just to encroach on the another technology topic, is how do these cores speak to one another? It's really basic to say it's memory, but actually there's technology out there that comes with the Linux kernel, which is called remote proc and RP message, and that's how these things communicate. And it's not just the Cortex-A to these heterogeneous cores. You can actually map endpoints between those different Cortex-R and Cortex-M cores. So you don't even have to really go through what you conceptually think of as the hub when I put those Cortex-A's in the center. You can do that point-to-point communication, which can speed things up as well. On the other hand, of course, when you're using something like, for example, ROS, it's not going to work that way, right? So ROS has the central messaging system to handle that sort of thing. But it's just an option, a design option.
And ROS, just in case anyone's out there that doesn't know it, robot operating system.
Yeah.
Just want to make sure, you know, we throw out some acronyms sometimes. But yeah, so cool. So I want to, we kind of alluded to this, but like, let's talk about some of the challenges that developers might face while building these types of systems and how they can overcome these challenges. And if we're digging too deep into your session, feel free to point people to that. But if you can share
I can
some.
just say this. I mean, look, when you start doing this, you're either going to come from, if you've never done heterogeneous or asymmetric processing work before, the first thing you're going to come from one of two backgrounds. You're either going to come from an application processor background working with Cortex-A's, or you're going to be coming from a microcontroller background working on Cortex-M's or Cortex-R's. And this is going to be an eye-opener. It's going to be a completely different shift in the way that you approach debugging, for example. How do I load my firmware onto my microcontroller core and update that firmware and operate it when I have Linux in the middle in the core as the Cortex-A, right? And what you begin to learn is that the Linux kernel is awesome. It provides remote proc and RP message. Remote proc is really for managing the life cycle of the firmware being applied to these small microcontrollers on the same die. And RP message is like a messaging construct that you use to talk to these different microcontrollers. Now, that alone is not a small learning curve, because what needs to happen is that every semiconductor manufacturer needs to write a driver for their topology. right? And how they want their customers to work with their system. So they need to write a driver. You need to learn how that driver operates. So we need to simplify that approach a bit. And there's actually a system out there that Xilinx heads that's called OpenAMP. And that simplifies the operation of asymmetric multiprocessing quite a bit. But I feel that we're not quite there yet because it's still a little bit challenging to digest. But it's much simpler than rolling it basically your own self, right? So the next step is really we need to simplify how we encourage developers to approach solutions for asymmetric processing. And that the patterns are helpful, but you need tools too. When you think of things like high performance compute, they have very high level frameworks like skeleton models, for example, that enable them to work with many different kinds of cores simultaneously and design these solutions. And I'm looking forward in the future to something like that happening, right? And that's where we need to progress to make the developer's life simpler.
And you kind of talk about some of these tools. It seems like in your session, you'll be talking about compilers and things like that.
Yeah, I'll get into details. I'm not going
Okay.
to talk about it here.
Yeah, no, that's good. In fact, reminder, everyone, we are giving a teaser right now for a session that Richard will be giving at ARM Dev Summit. So, we'll share the link again. There it is. Boom. devsummit.arm.com. Go register and then add this to your calendar. So this is a teaser. We're not giving you everything. Very cool. Thank you, Richard. So yeah, we just talked about right now some of the challenges facing developers who are building out these systems. So let's kind of start going into the FreeRTOS embedded Linux. How are developers using the cloud FreeRTOS embedded Linux to deliver these embedded Linux systems at scale, right?
Yeah,
so now we're kind of tackling AWS here, right? Because we're going into the cloud.
Right. Now, we can get like really complicated with a whole matrix of different scenarios that could be implemented, but I'm going to keep it very simple in this particular case where Linux is the one who controls the internet connectivity, right? So everything is going to be going through the Linux system. And really the reason, and then FreeRTOS would run on the microcontroller based course. And the reason for that is twofold. One is that FreeRTOS has been around now for 20 years, and people are very familiar with the APIs and how FreeRTOS is organized and how it works, right? It's it's a pretty popular real-time operating system, and it works across all these cores, all these ports for like the Cortex-R, Cortex-A, well, in this case, we're not running on Cortex-A on FreeRTOS, but Cortex-M. It just runs on those cores, right? So I can go install the kernel. Now, what's the big deal? If it's just I just want to write an app, right? Can't I just use bare metal? Well, not only are those APIs well known, and there's a lot of collateral that you can rely on for FreeRTOS, but it simplifies the way that you can tell certain tasks in the application in FreeRTOS how much they should be run based on the priority. Now, when you're thinking about something like a real-time system, we always want to ensure something like motor control to happen all the time. It has the highest priority, right? Any telemetry that I'm setting back to the application processor, it's less important than running my motor, right? So I still want that information to go, but it happens at a lower priority. Now, writing all those types of priorities and logging and all that kind of stuff without an RTOS is really challenging. But what I can say is that customers are already implementing or have been implementing for a long time. That was actually the first RTOS, I believe, used an open AMP, right, for the asymmetric processing. So it makes things very simple, long history. The API is easy to follow. The documentation is easy to follow. There's a couple of really great books that helps you from an API and also a concepts perspective. It's just all there.
Awesome. Well, yeah, I think you summarized it there. So that's good. Yeah.
Did I miss something?
No, I think you did good. In fact, I mean, the next question for me, at least, was what is AWS doing to help folks build out embedded Linux solutions? And it sounds like, this also is kind of in line with that, providing the documentation, providing the use cases, possible projects or demos, things that people can clone and build themselves to test stuff out. I mean, is AWS doing all this kind of stuff? Maybe you can add a few more things to the list.
Yeah, sure. So look, it's it's really easy for us to talk about the straightforward technology. Oh, implement embedded Linux. Oh, implement FreeRTOS. But really, I mean, a lot of the pain for developers and people who are delivering solutions to customers comes from the entire IoT product lifecycle, right? It goes all the way back from design to building to delivering to maintaining the solution, right? Especially if you're a company that's developing a global solution. If you're a company that's delivering IoT products globally and you need to send global IoT updates, it's probably easier to deliver those IoT updates through endpoints that exist globally. So you'll need a delivery mechanism like AWS to do that. And so I have another cheat sheet here about a major thing that actually started a little over a year ago. And I did training earlier this year at Embedded World, and we're doing more collateral around this. We have some GitHub repos on this, but it's really doing the entire CI/CD pipeline. Now, for asymmetric processing, it's not just doing the Yocto build in the middle here. If you're just doing embedded Linux, you just care about this. But if you're doing asymmetric processing, what we're talking about here, you actually have an additional piece that you need to work with. You need to build and stage those microcontroller firmwares as well, and do that in a safe way. So your Yocto build that can be done also in scale in the cloud can pick up the firmware. My fingers keep on going the wrong direction. Can pick up the firmware, put it in the Yocto build, and deliver it. Now, the interesting thing about here is when you're delivering at scale like this, not just sending it to manufacturing in your continuous delivery cycle, but you also need to think about system updates, right? How do you keep these systems updated across the globe? And what you have a couple of different choices at that point. You can either do things like the binary firmware update, which is the entire firmware update image, or a partial firmware update image, or you can use package-based updating, which is a choice as well. And so when you're bringing in your microcontroller firmware, you can actually get that build centrally in the cloud and then distribute that either in package repos up in the cloud or deliver that through another mechanism, such as using AWS IoT device client, which works with fleet management to transfer stuff from the cloud down to your devices. So there's a lot of options there. We're trying to build out these patterns and reference implementations in these GitHub repositories to help customers get started faster in developing these CI/CD pipelines up in the cloud. So it really takes a lot of the pain from the developer. For example, just one more thing about this is, if you've ever built an embedded Linux image, like gone and downloaded all the Yocto Pocky repos down your local machine and try to build it, and then you come back 3 hours later and maybe it's still running, right? Still compiling your Linux image. But I can take the same core image minimal, which is the minimum system in Pocky, and do that in the cloud in less than 20 minutes, right? And so there are special techniques that can save you time there that you can learn in these repos. I think the repo names are going to be given later. Special techniques that make rebuilds even faster. So if you have an application change, your rebuild turnaround time can be 3 to 5 minutes for continuous integration, right?
Yeah, I mean, I remember, so I've done several, I almost look at Yocto and Open Embedded almost like synonymous, right? But like Open Embedded, I remember doing bit bakes for Open Embedded not too long ago. I say that it's like several years ago. And, once you do a few bit bakes, it does cache those builds.
Yes.
And so the next time you build, it is quicker, slight modifications, adding a recipe or a layer here and there. Yeah, I mean, those of you who are familiar with building your own images with Yocto Open Embedded, you're probably familiar with what Richard is talking about. but definitely an experience. If you ever have an opportunity, I will say one of the coolest things I ever did at an ELC, which is an embedded Linux conference, they have these little side tracks, and it was taking like this intro to open embedded Yocto 101. Where I got to learn all these things. I took that home, built my own little open embedded Yocto images for my single board computers that I have back here. That was a lot of fun. It was a skill set that is worth acquiring if you ever have time.
Yeah. So when you have development teams that, say, for example, you have a two-piece team, like 12 people or whatever on your team, and they're all working on the same code base. Well, they don't all need to develop the Yocto image themselves either, right? So you can actually build that stuff centrally up in the cloud. If they need to have a cross-compile environment, the Yocto project exports an SDK. So you can have the cloud build the SDK for you, then your developers just download the SDK, install it, and then they have a cross-compile environment and start testing across their board. Just like that. I think John Simmons does a great job explaining that stuff in his training. So
excellent.
yeah.
Thank you. So we're pretty much at the last question I have here. There is a question in the chat that I'm going to take right after this. We'll try to tackle that. But so the last one here is I'm wondering, can you just give us a teaser? And I'm wondering if you already did, but I can't recall, on what demo you'll be showing at ARM Dev Summit. You already showed the board. Maybe you can give a little teaser.
Yeah, so the demo that I'm giving is on the AM64XX, right? And using those cores asymmetrically. What I'm doing is that I'm actually taking a demo that already existed that was provided by Texas Instruments, but I'll be showing some special techniques and using FreeRTOS on those Cortex-Rs. I'm not going to really give much away more than that, other than that you're going to be able to see in the demo how you can have bi-directional communication between those little cores and also the application processor. So when you think of situations like as needing to tell those little cores to do something or tuning a parameter, think of the scenario like, that core, I want it to be tuned a different way, or I have a machine learning algorithm that's going to take that data from that core, optimize, and then I need to send it back a parameter that's optimized, for example. You'll need that bi-directional communication, right? So I get into the details of that in the demo. It's super exciting. And I get to show how FreeRTOS optimizes that communication.
Excellent. That is very cool. And just a reminder here, I posted it one more time, devsummit.arm.com. Go check out the Tech Hub. Right there, you'll find Richard's section under there. So let's tackle this question, and then we'll go into closing out the episode. And I think this is more of kind of like an advice question here. It comes from Hibonics. He says, huge learning curve. His original question was, what happens if we come from both backgrounds? And I think this was when you were talking about embedded versus application, these two different layers, right? So his question / comment is, huge learning curve. I mean, I do both applications and embedded. So I cover both backgrounds. I need to be able to bring them both together. What happens if we come from both backgrounds? Maybe you can give some advice.
It was really challenging for me when I started that. So I was like, okay, I want to work against the microcontroller. What I want to do is I want to open up my IDE, and I want to be able to flash against that microcontroller and debug it using the IDE. It really doesn't work that way directly when you're doing asymmetric processing, right? So you have to really get used to taking the firmware that you're building, putting it on the Linux partition. You'll have a certain spot where the driver knows where it goes, putting it back in, and then debugging again, starting your debug session again. So you'll learn also when you have these asymmetric topology, well, these heterogeneous topologies, is that when you're using the debugger, instead of just seeing one core, or if you're using Linux, seeing like the symmetric compute cores together, you're going to see a whole list of cores. And when I first saw that, I was just like, oh my gosh. So I had to know which one to choose to debug and get debug information. Is it like on the AM64XX, it was like, there's R00, R01, R10, R11, keeping track of which one goes where for the behavior I need, because I have a user application on the Cortex-A's that need to talk to those cores. So I need to keep that all straight. And it's just a new ball of wax.
Yeah. So basically, Hibonics, good luck.
No, it's not that bad. It's not that bad, but it's, I didn't want to put it that way, but it's, look, that's why we need to make it easier. And the more that we get feedback from customers about where they're struggling and understanding how to do these things, the better we can make tools and experiences. It's as simple as that.
Yeah. Do you see his comment there? Head explodes. All right, cool. That I thought it was a good one. Here we have a comment here from John Moores. Let's just read it here real quick. So something like UC Linux with a Cortex-M should work, or if on the same chip as a Cortex-A7, like an STM32, then there should either be an API or write device driver to do so if not already provided. That's a lot to kind of rattle off there and digest. But thank you for sharing that, John. I don't know, do you want to comment on that?
Yeah, so I just never had come across the use case where I would run that tiny embedded Linux on a Cortex-M. It just never came up. But what I can say is that we do have folks running FreeRTOS on Cortex-M and on Cortex-A, right? And when you go to the FreeRTOS repos today on GitHub, it's github.com/FreeRTOS. You'll see the FreeRTOS kernel there. There is work happening right now for symmetric multiprocessing. So if you want to do FreeRTOS on Cortex-A's, it's there, right?
Great.
It's ongoing. It's early days, but it's happening now. So
excellent. Yes, we just shared the GitHub there, github.com/FreeRTOS. Hibonics does say thank you. Thanks a lot. And we did have one more question that came in here since we still have about 6 minutes left to the hour. Let's take this one from Alan Robertson. He asks, what would you say are the absolute necessities that an operating system should provide for IoT use?
So if we're talking about well, I'll just make it simple. You need connectivity, right? And you need to be able to manage that connectivity. You need to be able to fail confidently. When I say confidently, I mean when there is a failure on the radio, your application needs to be able to behave accordingly, either caching, logging, queuing, whatever you need to do, so you can replay the data that goes up into the cloud. Without doing that effectively with your radio, you're not really doing IoT on the embedded device. You need to be able to overcome that failure situation.
Excellent. There you go. Yeah, I like the connectivity thing, though. I think that's important.
Without that, there's no internet, so it kind of defeats the purpose.
I mean, the question was, what was the absolute necessity? And so, I mean, you did answer it very simply there. Okay. I don't see anything else flooding in here. Now it's the time where we start closing this out. So Richard, we give you an opportunity for a shameless plug. You can forward us, tell us about anything you like. Where would you like our viewers to?
So what I'm going to do is I'm going to share my screen real quick.
Okay.
And
let's bring that up.
I'm going to share screen, make sure I share the right screen. And what you'll see over here is a repository that we started working on a couple of years ago now. It was launched 2 years ago, actually, this month, called the Meta AWS project, right? This is a big layer for AWS device software. When you need to install the device SDK for C++, if you need to install Corretto, which is the long-term support JDK from Amazon, if you want to use Firecracker, which is some edge technology that's also used for AWS Lambda, that's all in this particular repo that you would add to your BB layers in your embedded Linux image. So you can install and run AWS device software. Now, we are a platinum member for both Yocto Project and Automotive Grade Linux. But what I'm really excited to announce what happened this week is that Meta AWS became Yocto compatible, which requires some quality testing by the Yocto project. So we just got that accepted this week, which is totally exciting. Now, besides this bit layer, we do have a couple of other repositories I'd like to briefly talk about. The first is one that we've been building up called Meta AWS CI when I was talking about continuous integration. This is the repo where we're going to put all those artifacts. There's a workshop in here, module 1 and 2 is ready. So if you want to go in there and take a look at those modules for doing continuous integration up in the AWS cloud, you can go check that out today. And those modules are going to continuously be built up over time. The last thing I would like to show you is the Meta AWS demos, which is a repository that we have that captures demos for specific types of hardware. The AM64XX demo isn't up there yet because I don't want to put it up there until the Dev Summit session happens. But you'll see other demos up there. The Raspberry Pi with AWS IoT Greengrass, for example. That's up there. So if you want to go build your embedded Linux images in a very simple way with these demos, they're all right up there for you to take a look at.
I think this has been one of the best shameless plugs we've had so far on the show. You covered a lot of ground there. So yeah, awesome. Thank you. Lots of things for you all to go check out, and we'll make sure that those links end up in the description of the video so that you can go click on them much easier. Here we have a few things coming in from our viewers. Hybotics says, great stream. He'll be back. I think that's thanks to you, Richard. Definitely not me. David W., great episode. He's one of our resident community members here, comes here quite often. So thank you, David. Alan, thanking you for your answer to that question. Oh, cool. So there we go. Let's close this out now. So Richard, any last words before I give this kind of closing ritual?
Yeah, so if I was going to say, if there's one thing that I'm super excited what I've been seeing ARM do lately, which is the new IP around CoreStone, right? So I don't know if you've heard about that or seen that, but when I saw the CoreStone 700, I'm like, when can I get embedded Linux on that? When can I start using that, right? So I would just say when we're looking at newer, like when I talked about these fit for purpose patterns, looking at specific topologies, that's what the CoreStone 700 and others do, which is putting together fit for purpose cores for use cases. So I'm excited.
Yeah, I definitely heard of it, seen some stuff on it. I think, gosh, I feel like there might be a session on it at Dev Summit, if I recall correctly. So I wouldn't be surprised if there was. Like, I mean, there should be.
Check it out.
Yeah, if there is, check it out. There you go, from Richard. Okay, well, then I'm going to close this out, Richard. First and foremost, I want to thank you just so much for taking your time. I know your time is so valuable, spending an entire hour here with us, plus the green room time. So thank you. Thank you, from ARM to you. Very much appreciate that. And thank you, AWS, for yielding that time as well. All the viewers out there, you're great. Gosh, thank you for spending the time with us as well. We know that you could have spent this hour anywhere else doing so many different things, yet you spent it here with us. Thank you. And all the people watching this on demand, we appreciate you as well. So we'll see you all next week. We have an exciting episode as well, as we do every week. We'll be meeting with Gordon Williams, who is the founder at Espruino. So make sure you check that out. We're going to talk about microcontroller development with Espruino. If you're not familiar, perfect chance to get familiar by spending an hour with us on Thursday next week at 5 p.m. UTC every Thursday. So I'm going to share this right here in the chat. You can go ahead right after we close this out, head on over to that link, set your reminders. Once again, Richard, gosh, thank you so much. Everyone watching, we'll see you next week. All right. Take care.
All right.
Enjoy your week.
Bye.